So let's start with section 4.3. In section 1, we got the basic definition of probability, and 2, we were dealing with what an event are. We're going to keep working with this idea of events and what happens if we have more events going on, getting us some rules for putting things together. So for this section, let's get this up here. We're going to introduce a notation we're going to use with probability and learn some of these rules for putting events together, basically. So here's our experiment. Our experiment is rolling a fair six-sided die. Our event is going to be roll an even number, so we're looking for the probability that we will roll an even number. That's too much to write. We're lazy. So our notation is like this. We would say P parentheses roll is even is 0.5. So this is what this notation looks like. We use P generally because we're talking about a probability. And we're going to say, so it's a like function notation, which is the probability function here. And my input is going to be the event, what we're looking for. So in this case, the probability of event A happening. So see if you can use that with our good old basic stuff we got from sections 1 and 2 and find these probabilities. What, 2, 4, 6. Pause the video, see what you can do. When you think you got them all written down, start the video back up and see if you agree with what I got. So I'm dealing with a fair 20-sided die. I'm just going to write out my sample space. This might make this easier. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So that's all my possible inputs from there. And I start working on these. P of 4 is the probability that I get a 4. There's only 1 out of 20. My probability is 1 out of 20 or 0.05. Probability that I'm less than 10. Are going to be those. It's not inclusive. I can't equal 10, so I have 9 numbers that are less than 10. So 9 out of 20 is 0.45. P odd. I'm looking for what's the probability that I'm going to get an odd number. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10. What am I doing here? 10 out of 20 or 0.5. If I want 4 or odd, that means all of these work and the 4 works. I got 11 out of 20, which is 0.55. My probability of being odd and less than 10, that means I have to look for the overlap where both were odd numbers and were less than 10. So that would be 1, 2, 3, 4, 5. Just those 5 numbers. So that would be 5 out of 20 or 0.25. Finally, odd or less than 10. That means I can take all these ones that are less than 10. I got 9 of them. And I got 10, 11, 12, 13, 14. So I have 14 out of 20, which is 0.7. So that's basically using that probability notation and putting it together. This isn't too bad to do. You might not have needed the sample space, but it helps sometimes. So let's see where we can go from here. So a couple things. When we looked at that, note when the probability of getting a 4 was 0.05, probability of being odd is 0.5, probability of 4 or 5 is 0.55. Hey, add those together. Hey, sweet. But here's the problem. Probability of odd was 0.5. Probability of less than 10 is 0.45. If we add those together, we don't get the probability of P or less than 10. So sometimes we can just add the probabilities together when we're doing an OR and get our answer, and sometimes we can't. And that's what we need to really look at here on these rules. We'll look at AND next lesson, I believe. So coming back to the sample space to kind of look at this and see what's going on. When we look at rolling a 4 and rolling odd, these are our numbers we get. And we're saying OR. Look, notice these are mutually exclusive. There is no overlap. But when we look at rolling an odd number and rolling a number less than 10, there is overlap between the two of these. These are not mutually exclusive. And that, I said that was in the last lesson, I said that's going to be important to us when we start combining these. And here's where you see why. It's much nicer when we're mutually exclusive. So we have our rules. Our special addition rule is if we are mutually exclusive. If there's mutually exclusive, there is no overlap. When we have A or B, we can just add the two probabilities together. Sweet. And this also works if there's more than two events. A, B, and C are mutually exclusive. Again, they all have to be mutually exclusive. Then we can just add all the probabilities together, no matter how many elements we have or events we have, as long as they are all mutually exclusive. There can be no overlap. So blah, 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 blah. This is what we just said. They don't overlap, so it's just like how many possibilities we're counting that. It's going back to our F over N. As long as we don't overlap, we're good. And so we can just count them together. However, when we do have overlap, we're not mutually exclusive. Notice we count the 9 for less than 10, but the 1, 3, 5, 7, and 9 are counted both when we count how many odd numbers we've rolled. Also, how many are less than 10. So these get counted twice, and that's what messes us up. Because there's overlap. Everything in that overlap gets counted twice when we are looking at possibilities. So we have to take an account for that. So we look at this. What's the probability of getting this overlap? This would be the probability of both being odd and less than 10, that 0.25. So if we add up all of these, add up all the odds, add up all the less than 10, subtract the ones that we counted twice, we get the right probability. And again, that overlap is the intersection of the two events. And that's going to happen when they're not mutually exclusive. If it is mutually exclusive, there's no overlap, so this is nothing. So here's our formal rule. This is general, so this works for any OR problem, any union problem. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Oops, let me go back. I want to say something more I don't have in the slide here. So, let's go on to this one here. You notice, if we're mutually exclusive, the probability of A and B equals 0. If it's mutually exclusive, there is no overlap. This crosses out, and we have the special rule. The special rule works only if they're mutually exclusive. But this kind of shows you the general rule will always work, because if they are mutually exclusive, then this will be 0, it pops out, and we got the special rule. So that's one nice thing. If you're not sure which rule to use the general rule. Because the general rule always works. That's why it's general. The special rule only works for mutually exclusive. So now let's get to our last rule. Last rule is the complement rule. Let's be nice to one. No. Complement rule says basically if the complement is anything that's not in A, so the probability of being A plus the probability of not being in A is everything, is 1. So the probability of not A is 1 minus the probability of A. That's the complement rule. If I know the probability of rolling a 4 is 0.05, probability of not rolling a 4 is 0.95. It's the complement. It's 1 minus that. So those are our 3 rules. So on here, I want you to again say which rule can you use. And when I'm talking about which rule, we're going to talk about the special rule, special addition. We're going to say general addition. And we will finally do the complement. So go through for each of these, figure out which rule you can use, and then find the probability after you've figured out which rule you're going to use on this. So pause the video, take a few minutes, figure these 5 problems off, start the video up going again. Okay, let's do it this way. Probability of Jack or 5. I don't need it that thick. So you can't be both a Jack and a 5 at the same time. So this is going to be one where we're just going to use this special rule. So we're just going to say what's the probability of being a Jack plus the probability of being a 5. There's 4 Jacks. There's 4 5s. We get 8 out of 52 or 2 out of 13. Probability of even or king. Again, you can't be even an even numbered card and a face card. So these are mutually exclusive. We're going to use a special rule. Probability of even plus the probability of being a king. Probability of being even, there are, 20 out of 52, because we've got 2, 4, 6, 8, 10 for each of the 4 suits. Probability of being a king, there's 4 kings. So we're going to get 24 out of 52, which would be 6 out of 13. I'm not taking these to decimal because they're awful decimals, and I don't want to mess with that. So as I said, generally we will give our probabilities either as a decimal or as a fraction. Fractions are fine. So we want the probability of a heart I gotta look back at that. What was that? Heart or a face card? Now here, we can be both a heart and a face card. These are not mutually exclusive, so here we're going to have to use the general rule. So we're going to have to say the probability of a heart plus the probability of a face minus the probability of being a heart and being a face card. So we have to use that general rule, take off this overlap. There are 13 hearts in your deck of cards. There are 12 face cards in your deck of cards. But how many hearts are face cards? There are 3 hearts that are face cards, so we have to subtract 3. You notice here, I didn't simplify because I'm adding these fractions. I may as well keep the common denominators. I could do this with just, we did with the sample space and counting them, and so we're just counting how many times it happens up here. 13 plus 12 minus 3 is going to be 22 out of 52, or 11 out of 26. Let's come to this one. Next one was the probability of... I can't read my handwriting, so I'll go back to here. Probability of not an ace. So here we're doing the complement rule. So this is 1 minus the probability of being an ace. And this one might be just as easy to do counting the other way, but we want to practice using these rules. So that's 1 minus 4 over out of 52 is going to be 48 out of 52, or 12 out of 13. If only they were all that easy, right? Last one, we have not a face card or a club. Now we got to be a little careful when we say not. What does the not apply to? We're going to say the not just applies to here. If I wanted to say not a face card or a club, I would put that in parentheses to say the not was dealing with most of them. Or to say not a face card or not a club. I'm not going to trick you that way. Well, maybe I am tricking you this way. Here, not a face card, we have the complement rule. But we're looking at are these two things mutually exclusive? Is it possible to not be a face card and be a club? Yes. So we got to use the general on here. So we're going to need the probability of not face plus the probability of club minus the probability of not face and a club. So we say, well, let's see, the probability of a face is 4 out of, sorry, not 4, 12 out of 52. So the probability of not a face, 1 minus 12 over 52. Probability of a club, there's 13 clubs. Not a face card and still a club. So we're looking at how many clubs are not face cards. So that would be 10 cards are clubs and are not face cards. It's almost more confusing on this problem to do it this way than it would be just to make the sample space. I don't know, maybe not. So this was 52 minus 12 is 40 out of 52, plus 13 out of 52, minus 10 out of 52 is going to be 43 out of 52. So this is basically using some of these basic rules of probability. Let's go back here. And then again, our basic rules we're talking about are the special addition rule, the general addition rule, and the complement rule are what we're kind of expecting you to be good with, and this notation. So I just want to finish off with this. With the special addition rule, it was really nice. I can extend this out to as many different events as possible. But for the general addition rule, it gets more complicated. So I'm going to give you the one for 3 events, and we're going to be good with that. But if we have 3 events, we can see from this diagram, we can do the probability A, B, and C. Add those together. That's special. But you notice, between A and B, these values are counted twice. So we have to subtract that intersection. A and C, these are counted twice. We subtract that intersection. B and C, these are counted twice. We subtract that intersection. However, this part in here is counted in all 3 of these. So we've counted these numbers 3 times. So we counted it 3 times, and then we subtracted it out once here, once here, once here. So we've subtracted it completely out. So now we have to add it back in again. So that's where we have to add the probability of A and B and C. So as we get more and more events, the general rule gets more and more complicated, and we might want other ways to look at that. But that's kind of where we're going to go for now. So here are some problems that you can work on.